Hello, there we go. Okay, so probability experiments. So I went over the basics in those videos, so we're going to continue from the basics with just a little bit of review. The idea of a sample space is always important. That's what you're working with. With the idea of a six-sided die, it's pretty simple sample space. 1, 2, 3, 4, 5, and 6. And then a moment ago, I rolled the die hoping for an even number. So what you're hoping for is called the event space. And that, for me, in this case, was 2, 4, or 6. And probability is always about counting. It's always counting favorable events and dividing by all events. Event space tells you what favorable events are. The sample space tells you what all possible events are. So in this case, I can count and get a 3 out of 6. Often with probability, we won't reduce it. We'll leave it that way because that tells me how big my event space is, which is nice to see sometimes. So although we could state it as 1/2, that's not as important. 3 out of 6 is pretty good. More often than reducing a fraction, you'll state it as a percent. So 50% or 0.5. Other kinds of probabilities that we see. So some probability events are discrete. Discrete means I can count each individual thing that can possibly happen, but some sample spaces are not countable. So for example, consider a spinner or maybe a dartboard. Look at both of those here. Suppose we have a circle and that point is in the center, and then we set an arrow on there to flick around. So let's see, I need tools. Let's make the arrow red. And then I brought some spinners for you all to play with. Where's my little box? There it is. Hopefully I have enough left. Oops. Runaway dice. All right, spinner for you.
So what did you say the sample space was?
Sample space is all possible events. All or outcomes, yeah. All possible outcomes. All right, so then here with our spinner, come on, there we go. Let's suppose it is split into 3 equal regions. Oops, I can't spell today. Can't spell any day, but that's okay. And by equal regions here, from the center, they have to have the same angle measure for each one to be equal, because that's what matters most here. So for example, if we're thinking about degrees, there's 360 degrees in a full spin. So that means each of these sectors of the circle has to have 120 degrees in it to be equal. And let's suppose that in this region we have the number 2, and that one we have the number 4, and that one I have the number 9. So what's the probability of spinning a number 4 here? One out of 3, because they're all equally spaced. So there's one area out of 3 equal areas. Okay, so like fractions being equal parts of a whole, that equal parts of a whole is still very important in probability. Similar example to this would be a dartboard. Where I can't really count, I have to look at areas instead. So suppose we have a circular dartboard. Let's say the center's right there. And let's suppose there's this little center area in the middle. And actually, I wanted to make that a little bit smaller. Now let's do that. And let's say the inner one, the radius is equal to 1. And on the outer one, radius, let's call it a capital R, is equal to 10. And I want to know what's the probability of hitting the inner circle. Now, there's not things to count like 1, 2, and 3, okay? Or the probability of picking a person, I can count the number of people. Here I have these whole regions I have to analyze, so I have to compare their areas. So I have to calculate the area of the region that's favorable to me right there. So what's the area of the inner circle? Well, it would be pi times its radius squared, right? And the probability, and let's assume that every dart hits the board, but it hits randomly. Like I'm not a good shot, but I can't always hit the board. How big is my board here? Pi times the radius squared again. So my area is favorable events, the inner circle, divided by the sample space, which is the whole dartboard. So same idea applies, it's just a different way of calculating because I can't count. That cleans up a little bit, right? The pi's divide out. 1 squared is 1. 10 squared is 100. So assuming that my dart will always hit the board, but it hits randomly on the board, I don't really have control over where I hit, then I have a 1 out of 100 chance of hitting that center circle, assuming there's no skill involved besides hitting the board. Okay, so that's a slightly different version of the probability. So what we're going to mess around with here is some experimental probabilities where we watch things happen. So for example, slightly easier version. All right, so there's a basketball net. And then here's me getting ready to shoot my ball in there. What are the possible outcomes here? I don't make it. What's the other one? Yeah, so either I make it in or I don't. So those are the two possibilities. So some would argue that, well, there's two options. So there's one chance of getting it in and, oh, I missed. I'm trying to throw dice into a basket over here, or I do make it in. So somebody might say it's one, oh, I didn't even get it in the room. It's 1 out of 2. Now, if that were true, then that means I could go up against some NBA star and I would be just as likely to get it in as he is. That seems pretty unlikely though, okay? Because they do that for a profession. So in a case like this, we can't just look at the situation and say, oh, it's 50% or 75% or 90% or 20%. We have to watch the situation and see what happens. That's why statistics are so important in sports. So in order to calculate this probability, the probability of getting it in, we would have to watch and we would have to look at the number of, let's call them hits, number of times in versus the number of shots. Right? So we get this free throw percentage based on that. So we're going to play around with this kind of experiment in a couple of different ways. I have some spinners that we're going to mess with for activities 1 and 2. And then in activity, we're going to skip 3. In activity 4, we're going to play rock, paper, scissors with a partner and see if we can determine both experimentally and theoretically what the probabilities of rock, paper, scissors are. Does everybody know what rock, paper, scissors are? Not sure? Oh, you're kidding? Okay. For those of you out there that don't, we better, let's see if, I bet Wikipedia has an article on rock, paper, scissors. They have an article on everything. Rock, paper, shotgun. What? I've never heard of that one. That's interesting. Rock, paper, scissors. Look at that. Wikipedia is the first hit. So rock, paper, scissors, you and a companion throw down, and either you throw scissors, 2 fingers, paper, a flat hand, or rock, a fist. And let's see, how's it go? Scissors cut paper. Paper can cover a rock, and a rock can crush scissors. Okay. You throw some random thing in and mess it up, and I have not heard of that, but my kids probably know about it. Okay, so we're going to do rock, paper, scissors eventually, but first let's take a look at the spinner activity. So I'm going to bring that up here. Let's see, we are in chapter 9, activities. And so what we want to do is find somebody to spin with. And then you'll have somebody will play spinner A, somebody will play spinner B. And what we want to do is keep track of, for example, for spinner A, how many times did you get a 2? How many times did you get a 4? How many times did you get a 9? Okay, so that's the first part. The second part is comparing spinner A and spinner B. Okay. So if spinner A gets a 2 and spinner B gets a 5, spinner B wins. On the other hand, if spinner A got a 9 and spinner B got a 7, spinner A wins. So we want to keep track of what is the theoretical probability of, say, getting a 2, a 4, or a 9. For B, we want to keep track of what is the probability of getting a 3, a 5, or a 7. And then we want to compare, if we played one-on-one, who wins more often. Okay. So any guesses as to who's, like, if you get to pick first, which spinner were you going to be? Would you pick spinner A or would you pick spinner B? It doesn't matter? Okay, so we have it doesn't matter. Anyone else? My dog would pick spinner A because it has the highest number. My daughter would not pick that because it has the lowest number. Maybe it doesn't matter. Let's find out. So again, one person will be spinner A. They will keep track of the A's. So the way I'd recommend it is the tally sheet we're not going to use right away. So what you'll do is you'll play against each other. And I think everybody should be a secretary in this. And then what you'll have is a table that looks like this. The turn, what happens for A and what happens for B. So like first turn, maybe A gets a 2 and B gets a 5. Second turn, A gets, say, a 9 and B gets a 7. Third turn, A gets, I can't remember what A's other number was. Can somebody tell me? Spinner A, anybody have it in front of them? 2, 9, and 4. So maybe A gets a 4 and B had a 3, I believe. Okay, so you're just going to repeat this over and over again. How many times did we look for? 20? Is that right? 30 times. So you'll have a table with 30 rows. And then we'll look back at the table and say, okay, how often did the 2 come up for A? How often did the 4 come up? How often did the 9 come up? Okay. If our spinner is designed right, about how many 2s should we expect to see out of 30? 10 of them, because 1/3 of the numbers are 2. Yeah, is what we should expect to see. So there's another idea floating around here called expected value. All right, so I'll cut this boring chunk out of the record. Actually, I think I'll stop the recording and then restart one in just a little bit. We'll come back with more on the spinners.